What specific problem does the PODS framework aim to solve in the context of reinforcement learning for large language models?
The PODS policy optimization with downsampling framework aims to address the computational asymmetry inherent in reinforcement learning, RL, for large language models, LLMs, particularly during the policy update phase. This asymmetry arises because the inference phase is highly parallel and efficient, while the policy update phase requires extensive synchronization and memory, leading to bottlenecks in resource-constrained environments. By selectively training on a smaller, more informative subset of rollouts generated during inference, PODS maximizes resource utilization and mitigates communication overhead during policy updates. The framework employs a strategic downsampling method, specifically max-variance sampling, to ensure that the selected rollouts provide diverse and contrastive learning signals, thereby enhancing the model's reasoning capabilities. Ultimately, PODS improves the efficiency and effectiveness of training in RL for LLMs by focusing on the most valuable rollouts rather than processing all generated rollouts.
How does the PODS method work? Please illustrate the process step by step, including how rollouts are generated, selected for updates, and how advantages are calculated.
The PODS policy optimization with downsampling method operates in a structured manner to enhance the efficiency of reinforcement learning for large language models. First, it generates a large number of rollouts in parallel during the inference phase, where each rollout is produced by autoaggressively sampling from the policy parameterized by theta, resulting in a set of n rollouts. Next, instead of using all generated rollouts for policy updates, PODS employs a downsampling rule to select a smaller subset of m rollouts based on their rewards, utilizing strategies like max-variance downsampling to maximize the diversity and informativeness of the selected rollouts. After selecting the subset, the advantages for these rollouts are calculated using the formula A_SI equals R_I mu_S sigma_S, where mu_S and sigma_S are the mean and standard deviation of the rewards from the selected rollouts. Finally, the policy is updated based on these advantages, allowing for more efficient training while reducing communication and memory overheads during the policy gradient update phase.
Can you provide a simple example to demonstrate how the max-variance downsampling method selects rollouts based on their rewards? Walk through the algorithm steps with your example.
To illustrate the max-variance downsampling method, consider a scenario where we have 5 rollouts with the following rewards: R_1 equals 2, R_2 equals 5, R_3 equals 1, R_4 equals 4, R_5 equals 3. The goal is to select a subset of size, m equals 3, that maximizes the variance of the selected rewards. First, we sort the rewards. R_3 equals 1, R_1 equals 2, R_5 equals 3, R_4 equals 4, R_2 equals 5. According to the max-variance downsampling rule, we need to select the highest and lowest rewards to maximize variance. We can choose the 2 highest rewards, R_2 equals 5, and R_4 equals 4, and one lowest reward, R_3 equals 1. Thus the selected subset is S equals 1, 4, 5 with rewards 1, 4, 5. Next, we compute the variance of this subset. The mean of the selected rewards is mu_s equals 1 plus 4 plus 5, 3 equals 3, 33, and the variance is calculated as text var s equals frac 1 to 3, 3 squared plus 4 to 3.33 squared plus 5 to 3.33 squared, 3 equals 2, 33. This process demonstrates how the max-variance downsampling method effectively captures diverse learning signals by selecting both high and low rewards, thereby enhancing the model's learning from contrasting examples.
What are the key advantages of using the PODS framework over traditional GRPO in terms of computational efficiency and scalability?
The PODS framework offers significant advantages over traditional GRPO by addressing the computational asymmetry inherent in reinforcement learning for large language models. Firstly, it allows for the generation of a larger number of rollouts in parallel during the inference phase, while selectively updating the policy based on a smaller, more informative subset, thereby maximizing resource utilization and reducing memory overhead during policy updates. Secondly, the introduction of max-variance downsampling enhances the diversity of learning signals by capturing both high and low reward examples, which traditional GRPO does not prioritize. This strategic selection method leads to improved training efficiency as it mitigates the communication bottlenecks associated with gradient synchronization. Overall, the PODS framework not only retains the core advantages of GRPO, but also significantly enhances scalability across various hardware environments.
Describe the validation process used to assess the performance of the PODS framework. What benchmarks or metrics were utilized, and how do they demonstrate the method's effectiveness?
The validation process for assessing the performance of the PODS framework involved conducting experiments on the GSM-8K dataset, where the proposed max-variance downsampling method was compared against the original GRPO method. The Qwen 5-3B instruct model served as the base for fine-tuning, and both GRPO and GRPO pods were evaluated on the test set every 100 training steps. The training utilized a rule-based reward model that scored each rollout based on correctness and format, with specific hyperparameters set for both methods. Results indicated that GRPO pods consistently outperformed GRPO in terms of accuracy over the same training time, with the performance gap widening as training progressed. This demonstrates the effectiveness of the PODS framework in enhancing reasoning capabilities, as evidenced by improved performance metrics on the GSM-8K benchmark.
What limitations did you identify in the PODS framework that might affect its application in broader contexts, such as other types of reinforcement learning tasks or different model architectures?
The PODS framework, while effective in enhancing the efficiency of GRPO for reasoning tasks, may face limitations when applied to broader contexts. One potential limitation is its reliance on the max-variance downsampling strategy, which, although designed to capture diverse learning signals, may not be optimal for all types of reinforcement learning tasks that require different sampling strategies or reward structures. Additionally, the framework's performance is contingent on the specific architecture of the large language models used. Thus, it may not generalize well to other model architectures that do not align with the assumptions made in the PODS design. Furthermore, the computational efficiency gains observed in the context of GRPO may not translate to other RL algorithms that have different computational demands or structures, potentially limiting its applicability. Lastly, the effectiveness of the downsampling techniques may vary based on the nature of the datasets used, particularly if they are significantly noisy or unbalanced, which could hinder the overall performance in diverse real-world scenarios.